Welcome to the webinar, Opportunities to Decarbonize Offshore Platforms, Reality versus Rhetoric. My name is Chris Robinson, and I'm a Senior Director here at Lux Research, and I'll be moderating today's session. Presenting today is my colleague, Karthik Subramanian, analyst here at Lux Research. Throughout the webinar, you can type any questions you have in the questions box on the screen. Time permitting, we'll get to all the questions that we can, and if your question doesn't get answered, please don't hesitate to email it to questions@luxresearchinc.com, and we'll make sure to respond. And if at any point you have technical difficulties like a frozen screen, just make sure to refresh your browser and check that you have a strong internet connection. And with that, we can dive into the conversation. Over to you, Karthik.
Thank you so much for the introduction, Chris. Before we get into discussing the potential solutions to decarbonize offshore platforms, I think it's important to start off by asking ourselves this question. What's the purpose or what's the driver behind offshore electrification? Is it only decarbonization? And from the outset, it would seem so, because offshore platforms have always been associated with producing a lot of carbon emissions, and these carbon emissions mainly come from power generation assets on the platform. Most of your emissions, almost up to 85%, comes from power generation equipment on the platform. So any solution that's associated with the electrification of a platform will directly serve in decarbonizing the offshore platform itself. But it's important to understand that electrification is not just about decarbonization. It's about differentiation. Electrification enables the modernization of equipment that not only helps optimize existing activities on the platform, but also maximize revenues from oil revenue. And this oil production is now lower carbon oil production. And therefore, decarbonization in reality, or electrification of an offshore platform, is not just to reduce the carbon emissions, but that adds on to the efficiency improvements on the platform as a bonus. Now, if we look at the status of electrification, electrification is not a new concept, right? Equinor, one of the oil and gas companies from Europe, is one of the best examples of this. And their Hywind Tampen platform, of course, is one of the first offshore platforms that is being powered by floating wind power. But even a company like Equinor has now started questioning whether electrification is necessary, given how capital intensive it is and how not profitable it is at this moment in time. Now, it is important to note that despite agreements to reduce offshore emissions by about 50% by 2030. This is a target set by the Norwegian government alongside Equinor. What is driving this profitability concern is not the unavailability, or I should say it's not the lack of performance improvements from the electrification infrastructure, but rather any capital that's gone into electrification has not justified oil revenues because oil prices remain low today. So the main concern behind the lack of profitability is not down to the equipment itself that's enabling electrification. And while Equinor has taken a step back, this has not stopped other companies from continuing to pursue efficiency improvements on the platform. Chevron's Anchor project is a great example, where they have completely designed an all-electric facility with electric controls, motors, actuators, and equipment that have enabled the optimization of its operational activities while maximizing margins from oil production. As mentioned earlier in the webinar today, the production of lower carbon intensity oil as a result is a bonus on top of efficiency improvements. Not to mention, the influx of AI into modern workflows is going to be extremely relevant to offshore platforms as well, because AI, if implemented in the future with enhanced capabilities, can help operations become even leaner, helping oil and gas companies maximize revenues from offshore operations. So in today's webinar, we will be looking at potential low carbon solutions that can enable the electrification of an offshore platform. And we will also develop a framework that can help strategists devise a path to get to 100% low carbon platforms. we will use this framework and apply this to an offshore platform as a case study to understand how the thought process should be when it comes to selecting solutions. And finally, what this means in terms of potential solutions looking forward. Let us start with the low carbon power solutions. To begin with, offshore platforms today are run by simple cycle aeroderivative gas turbines. Gas that is produced alongside oil or associated gas is used for power generation. There are two directions of solutions that can be pursued. The first direction consists of transformative solutions that completely move away from any fuel-based power generation source. This includes offshore wind power, which could be either fixed or floating, wind turbines. You can also think about other new solutions like wave energy or even offshore nuclear power that can enable the powering of offshore platforms. The second set of solutions includes fuel-based solutions that replace a part of the existing equipment on the platform itself. For instance, you could think about running fuel cells on board an offshore platform, or you could also think about just replacing the fuel that is used in the gas turbine. This could be by blending low carbon hydrogen or low carbon ammonia with the existing gas infrastructure and producing power from that. The objective of these solutions is to ensure that you maximize utilizing existing equipment on the platform as much as possible. Now, what we have looked at the potential solutions, and we will now move to understanding how to select the best solutions that are suitable for your platform from this set. In order to select the solutions, Lux has developed a framework involving two plots and three parameters. The first parameter is the levelized cost of electricity ratio, or the LCOE ratio. This represents the ratio of the levelized cost of electricity produced from the new solution replacing the gas turbine to the cost of electricity produced from the gas turbine itself. And we plot this on the x-axis of the first plot. And on the y-axis, we have the emissions reduction potential of that source. In order to select a solution that's the best suited for this platform or for any platform in question, the solution that is being considered should have the lowest possible LCOE ratio, which means it's the most economical solution available among this, the set of solutions, and should also have the highest emissions reduction potential, which means the solutions that are of interest to us all lie on the top left-hand quadrant of this chart. Now, it is important to note that emissions reductions alone is not the driver, right? So what we do is we also consider space on the deck. If you look at the image on the right of this plot, you can see that offshore platforms are highly dense, very space-dense platforms. There is a specific deck on the platform where power generation equipment is installed, and there is hardly any extra room for adding additional equipment. Therefore, any new solution that is considered to either replace this the gas turbine on the platform entirely needs to also take into account the space availability on this platform. In order to do this, Lux has considered the third parameter called the spatial energy density ratio, which is the ratio of the power that can be produced from the replacement solution to the space it occupies, and how this compares to the power generated and the space occupied by the gas turbine that is going to be replaced. Again, similar to the previous plot, the solutions that are on the top left-hand quadrant of this plot, that is, solutions with the spatial energy density that is comparable to that of the gas turbine and having the lowest possible additional cost, is to be considered for charting suitable solutions. Please note that this framework only applies to solutions that are using the space available on the deck. So for example, floating wind will not be plotted on such a chart because floating wind turbines will be deployed outside the platform in the open sea. So with these charts, let us take in an example platform and see how we can think about charting strategies. For this webinar, we have chosen the Petronius platform that is operated by Chevron in the United States. It is 208 kilometers southeast of New Orleans and has been operational since the early 2000s. This platform, during its peak performance, used to produce about 70,000 barrels of oil a day, but has since used up oil resources and was estimated to produce around 6,000 barrels of oil per day in 2017. Based on this production rate, the platform that we will be considering for this analysis is considered to have 5 megawatts of power demand, and this will be used to chart the different solutions. Another point to note with the Petronas platform is that it is considered a potential candidate for carbon dioxide assisted enhanced oil recovery. Already there are discussions ongoing for connecting carbon dioxide pipelines that transport carbon dioxide from the state of Alabama to the platform itself in order to sequester the carbon dioxide while enhancing oil production from the site. With this in mind, let us look at how the different solutions would apply in helping this platform electrify. If you look at the first plot, which is considering the levelized costs with the emissions reduction potential, we see that post-combustion carbon capture comes up trumps, and it is at the topmost left part of this chart. Again, with carbon capture retrofitting, if this is not a solution that is being considered, the second solution to think about would be retrofitting or fuel switching. Fuel switching, if not completely possible today to 100% fuel because of the costs involved, could think about just blending low carbon fuels such as green hydrogen or ammonia at about 20% blending ratios by volume, because that is the restriction for transportation and storage today. These solutions could potentially help decarbonize the platform to an extent while utilizing existing infrastructure. But as we mentioned earlier, it's not just about emissions reductions. It's also about considering space on the deck. And here is where carbon capture becomes very difficult to implement, given it has a very low spatial energy density ratio. Point source carbon capture systems occupy a lot of area and therefore might be impossible to introduce them in a setting which is highly space constrained. This leaves us with fuel switching as probably the best option if fuel-based solutions are considered for the deck. The initial strategy would be to start off with blended fuels before moving towards pure fuels, depending on cost evolution. A second option to enhance the efficiency improvements on this platform would be to think about solutions such as waste heat recovery, or moving to completely electrically operated equipment that improves the energy efficiency and reduces the power needs on the platform. One thing to consider here with carbon capture is that while it is true that there are space challenges, carbon capture might still work for the Petronas platform because the Petronas platform is being considered as a candidate for carbon dioxide assisted enhanced oil recovery, which means there will be infrastructure surrounding the sequestration of carbon which is going to be built, which could mean that an additional platform where a carbon capture system could be retrofitted could be installed. And therefore, while it is not the most suitable solution on paper, it depends on surrounding infrastructure as well. Now, moving on to transformational solutions that are completely non-fuel based, on paper, offshore solar and point absorber wave energy converters seem to be the best possible solutions to help decarbonize the Petronas platform, given its load requirements. Now, with these two solutions, there are some caveats. A, offshore solar is yet to prove durability in harsh sea states for long periods of time. And at the same time, if we move this to wave energy converters are also have also not proven the offshore durability and storm survivability in harsh sea states, barring a few pilot projects in in uncontrolled environments. The Bureau of Ocean Energy Management in the United States states that there is no practical wave energy resource available at the Petronas field to deploy wave energy converters. This leaves floating wind as the possible best solution that is suited to powering the Petronas platform. Shore power in this regard becomes really expensive because of the distance from shore, and offshore nuclear could be a wildcard for this platform. But apart from the one floating power plant that was operated in Russia, the academic Lomonosov, floating power plants for civilian power generation is not the norm today. And there are no regulations that define how floating power plants can be used for industrial or civilian power generation applications, and therefore remains far out. Now, after all of these solutions, what are the other things to consider when devising strategies for offshore platform electrification? The first parameter to consider is the role of energy storage. Energy storage becomes extremely relevant to offshore platforms, particularly when considering transformational solutions that are not combustion based. In such instances, the power generation deck on the platform is to be completely repurposed to become an energy storage deck that houses batteries or any other form of energy storage that can support the reliability requirements on the platform. A second solution that is to be considered while electrifying offshore platforms is the use of power barges. If solutions that are being considered in the low carbon strategy is to decommission the existing gas turbine, power barges can help offset this period of no revenue when the gas turbine is not in use. These power barges can be directly plugged to the platform, enabling the continuation of oil production while the gas turbine is being decommissioned and the new solution is being introduced. The next parameter to consider, especially when it comes to switching fuels or blending low carbon fuels, is the question around whether these fuels are to be piped from shore or if onboard storage on the platform is necessary. Based on Lux's analysis, piping fuels is the most suitable option for offshore platforms, given how space constrained they are. However, the storage of fuels or piping of fuels depends on not just technological developments within transportation and storage of low carbon fuels, such as hydrogen or ammonia, but also the evolution of the low carbon fuel economy. The evolution of the low carbon fuel economy will determine which fuel is predominantly being considered for offshore applications, which will help clarify the doubt around fuel storage or fuel transport. And finally, the most important thing to consider, especially with retrofits, is the space requirements for post-combustion emissions reduction solutions. And this does not just apply for point source carbon capture systems, but also for other solutions such as selective catalytic reduction systems, which will become extremely relevant if switching to complete combustion of low carbon fuels, such as ammonia, where NOx emissions are a big challenge. So the combination of all of these solutions and considerations are important while devising a strategy for your platform. Now that we have looked at all the potential solutions, let us look at what this means in terms of an overall picture. The first conclusion to derive is that blending low carbon fuels or retrofitting existing systems and implementing energy efficiency measures is the best possible solution for existing offshore oil and gas platforms to electrify as well as decarbonize, given this works very well around the space constraints on such systems. If looking at new systems, or if new offshore oil and gas systems are being built, or if combustion is not viewed with the same importance for oil and gas platforms anymore, think about moving to shore. And by that, I mean connecting your offshore oil and gas platform to shore power. Shore power, again, will be economical depending on the distance from shore for the platform itself, but is a solution that is the most practical among the transformative solutions today, given that the question is around costs and not about technical feasibility. For those thinking about solutions that are outside the norm, wave energy remains a wildcard that can support remote power generation within the next 5 years. As explained earlier today in the webinar, Wave energy still has to prove that they can survive storms and can prove offshore durability, especially when deployed for multiple years. There are several startups, almost about 60 startups, that are active in the space, actively trying to test these systems in uncontrolled offshore environments. And therefore, within the next 5 years, we will have some clarity around the role of wave energy when it comes to supporting offshore platforms and powering offshore platforms. Monitoring is advised for the next 5 years, given they still have to go through multiple cycles of testing. So the key takeaways for those who have attended this webinar today is that number one, offshore electrification is not just about decarbonization. There is a lot of room for offshore oil and gas platforms, especially with the introduction of new software solutions like AI, to not just maximize revenues, but also modernize your existing equipment and differentiate yourself from the competition. If pursuing offshore electrification strategies, it's important to note that it's not about wholesale system changes at this moment, but about stepwise improvements that let you achieve your goals with time. And finally, low carbon power strategies are not about implementing them today, but these must be considered with a 10+ year horizon in mind. This is specifically because there are no regulations today worldwide in several places that require offshore oil and gas platforms to decarbonize. And the objective of strategists, must be to stay ahead of potential future regulations and be dynamic as an organization while improving the efficiency of your offshore operations. Thank you very much for joining the webinar today. I hope you found this useful, and we are happy to take questions now.
Yes, and thank you, Karthik. We'll now be taking questions that you might have on the presentation, which, as a reminder, you can type into the questions box. And if we don't get to your question, we'll be in touch after the webinar as well. So unsurprisingly, we had one question come in around marine power, a couple actually. What is the traction, market traction with marine power? What is the current status of marine energy / wave power? And what do some of the timelines look like for deployment and assessment of these solutions?
Yeah, thank you for the question. Marine power is kind of an interesting technology when it comes to just low carbon power generation in general, because it has had some waves, pardon the pun, of investment and progress, and then troughs of complete oblivion, where no one knows what's going on within the space. Right now, most of the companies that are active within marine energy, specifically wave power, are focused on trying to understand what it takes to improve the offshore durability and storm survivability of these systems, which remains a big bottleneck for not just reducing operational costs, but also proving the economic viability of these systems. For assessment timelines, we recommend 5-year timelines until 2030. And this is because a lot of these startups are right now testing their systems in uncontrolled environments. They're going through multiple cycles or iterations rather of technology development. And a few projects have already been announced that are pre-commercial. For example, Core Power Ocean has announced its project in Portugal and has been working on an active system. So there is not much traction that way, as there are still doubts as to what the long-term outlook looks like and whether they will prove storm survivability. But it could be that wild card that completely changes offshore power generation. Today, they're mostly restricted to powering small island communities or niche applications such as subsea sensors, where your power requirements are not critical.
Understood. And then another question came in around fuel switching, specifically how practical is fuel switching and which fuels are the best option if you go with an alternative fuel?
Right. This is one of the questions that we internally discussed as well during the development of the report on low carbon power strategies. And as things stand, the best fuel that would work if you're thinking about fuel switching remains to be anything that is methane based, whether that is renewable natural gas or if that is e-methane, probably biogas as well, because transport of hydrogen or ammonia seems to still take a backseat technologically speaking, and you don't have enough options for storage. So the options right now, and here we are not considering costs, right? So the best option, technically speaking, would be to stick to solutions that are as close to natural gas as possible in terms of composition. Blending of fuels up to 20%, especially hydrogen, is possible for piping. This is something where extensive studies have been conducted by the likes of TNO, the Public Research Organization in the Netherlands. And that could be an idea. But this also depends on where your offshore platform is located, right? If your offshore platform usually relies on tankering of fuel, whether that is produced oil tankered or if it is piped. And so that will also dictate how fuel switching works. So as things stand, as I said, long answer short, the focus should be on more natural gas-based solutions.
Excellent. Well, thanks for your perspectives there, Karthik. And that concludes our webinar for today. So the slide presentation and the recording will be sent to all attendees via email, should be in your inboxes later today. After leaving, you'll be prompted to complete a survey in today's presentation. We do appreciate any feedback you might have. It helps us improve and inform future webinars. So take a moment, check out our upcoming webinars on our website. Thank you for joining us and have a great day.
Thank you.